It's actually a pretty interesting way of solving line integrals. I'm not going to go into the proof, but you can find a proof in the textbook if you want to check it out. So here's what Green's theorem says. Suppose that we have a piecewise smooth closed curve that is the boundary of a region R, and that curve is our path through the vector field, right? As long as it's oriented so that the region is on the left, so if we're going in a counterclockwise direction, and F1, F2 is piecewise smooth, then we can use what's called Green's theorem, which converts the line integral into a double integral over the region R of, this guy should look familiar, that's the curl. We already know how to calculate the curl. We already know how to do double integrals. So this is actually taking two things that we've already done and putting them together. That's all this is doing. So, you know, we might need a little refresher on double integrals. It's been a little while. But other than that, that is the main crux of this section. So we're going to revisit a problem that we saw last time. This was on the last worksheet. It's actually on this worksheet too. So if you remember, we looked at this one last time and we split it up so that we parameterized each path of the triangle, and we did each leg of the triangle separately and added up the contribution of each. And I think we got -1 for the definite integral. This is a perfect candidate for Green's theorem. Because if we look at our region, so our region in the XY plane was basically connecting these 3 points. Like so. And we went in the order that the points were listed, which is this direction. So what Green's theorem says is, because we have a closed path, it makes a region inside it. So that would be our region of integration. So this is our region inside this triangle. Now, Green's theorem specifically does say that it has to be traversed in a direction so that the region is always on the left. It's not a big deal. If we were going the opposite direction, we would get the same magnitude, but the opposite sign. Okay, so it's not a requirement to have that, and in order to use Green's theorem, we just need to be aware of it, right? If we're going the opposite, if we're going in a clockwise direction, then we have to realize we're actually getting the opposite sign of the line integral. That's all. Okay, so we did this one before. We got -1. Let's talk about how we do it for this one. Well, two things we need for Green's theorem. Number one is we need the curl. Number two is we need our limits of integration. After that, it's doing a double integral, which we have a lot of practice at this point. So if we look at our vector field, which, you know, we have x, y, comma, instead of writing it as negative, the quantity of x minus y, why don't we distribute that negative and write it as y minus x? All right. So same vector field. We need the curl of this thing. We've done curl before. So the curl is going to be dx of f2, so y minus x, minus dy of f1, or xy. So ddx, what do we have? Well, y is a constant, so that's 0. Derivative of negative x is -1. And then here, dy of xy is just x. So -1 minus x. So as of right now, we've already got our integrand. It's the curl. Right? Again, we've been finding the curl for a while, right? That's nothing new for us. We find the curl, and now we do the region of integration for our limits, which again is something we've done before. Now we haven't done it in a couple weeks, but it's not new to us. And we have our choice. we could go bottom, we could do it in terms of y first, but if we look, the top and bottom are different here than here, which means we would have to split it up into two integrals. So let's go left to right first, and let's put these points on here. That's -1, 0. That's 1, 0. And this guy up here is 0, 1. So this would be y equals x plus 1 if we were doing it in terms of y, which we just said is probably not, there's not a problem with it, but we would have to do it as two separate integrals, right? That's kind of user preference on that one. And this one here is y equals 1 minus x. All right, well, because we want to do left to right first, we want to integrate with respect to x first, we need these solved for x. That's all. Both of them are invertible. So over here, x equals y minus 1. And right here, x equals 1 minus y. All right, so again, this is more of a refresher because this is stuff we've done before. You'll get, and this will actually be a good refresher on double integrals in this section. All right. So lower limit, upper limit. So y minus 1 to 1 minus y. That takes care of, 1 minus y. So that's our dx. That takes care of left to right. Now we just go bottom to top. Well, y is going from 0 up to 1. And there's our definite integral. All right. Next step would be to calculate this by hand. Again, because we've done double integrals in here, I'm not going to waste your time watching me solve a double integral. So let's bring in Symbolab. And I've already got it put in there. We know what it should come out to be. And big surprise, right? There's our -1. That's how Green's theorem works. It's another way of solving line integrals. Now, just a couple things I want to point out with Green's theorem. Number one, like we already said, it is not absolutely necessary to go in this counterclockwise direction. If we're going the opposite direction, it means we're just getting the opposite sign. So whatever we would get. So in other words, like if this had been going the opposite direction and we got -1, the line integral would actually be +1. Okay. The other thing I want to mention about Green's theorem is it does say it has to be a closed region in order for Green's theorem to work. Let's say you don't have a closed region. Okay. For example, I'm just kind of making this up, but let's take even just this one. Let's just say all we had was these two legs of the triangle. We had this guy and this guy. So we're starting here and ending here. And let's say we still say, hey, Green's theorem is still probably going to be easier. What we can do is we can close this by adding in this bottom part of the path. Calculate the whole thing using Green's theorem. And then we'll just find the line integral on just this path here and subtract it out. Okay. So it doesn't have to be, I mean, that's not something we're going to encounter in here, but I just wanted to make you aware of it because it says it in the theorem. There are instances where it might be easier to make it to use Green's theorem and then just find a little line integral on the part that you use to make it a closed region. And sometimes that's actually easier than doing the straightforward line integral. So we now have three ways of calculating line integrals. We have it via parameterization, right, and dot product. We have it via the fundamental theorem, which we can only use if we have a gradient field. And then we have Green's theorem, which is most useful when our region is easy to put in terms of limits. Okay. So one of the things that you're going to want to do as you prepare for the final is think about when you're using which method, right? Because you might get a problem with the final that just says calculate this line integral. And so part of what you're doing is deciding which method you think is going to be easiest. right? So as you go through the homework, think about, hey, why am I using Green's theorem on this? Oh, because my region is a triangle or it's a circle, and it's very easy to set up as a double integral. And think about this too. One of the things we had to calculate to do Green's theorem was the curl, right? Remember, if the curl comes out to be 0, what method are we going to use? If the curl comes out to be 0, what do we know about our vector field? It's conservative, therefore it's a gradient field, therefore there is a potential function, therefore we can use the fundamental theorem of line integrals. So then, and since finding the curl is actually part of doing this one, if we get a 0 curl, we know we can use the fundamental theorem of line integrals. Furthermore, if we get a 0 curl and we have a closed path, we know the answer is already 0 because we're starting where we're ending, which by the fundamental theorem of line integrals says is 0. Just kind of bringing all 3 sections together. All right. Then we've already talked about the curl test. This is actually nothing new for us. Remember, if we said the curl is 0, then obviously Green's theorem would give us 0 if we're on a closed path. But again, if we know that so 2 things. If we get a curl of 0, number one, if we have a closed path, we know the line integral is 0, unless that closed path encircles a hole. That's the only time we lose that guarantee. And the other thing is, if we have a non-closed path, right, or just a path between 2 points, if we get the curl is 0, we have a vector field, a gradient field, which means we'll probably use, the easiest will be to use the fundamental theorem of line integrals. So find a potential function evaluated at our ending point minus our starting point. Okay. Now, we also have a flux form of Green's theorem. So flux is the amount of something going through a surface. So imagine water flowing through a surface. All right. What the flux is it accumulates the rate and measures the amount of it going through. So we're going to look at flux integrals. We're going to talk about them a little bit today, and we'll talk about them a little bit more, not on Thursday, but on Tuesday when we look at surface integrals, because we'll look at flux integrals in 3D. Right now, we're only looking at 2D vector fields. Okay, so this only applies for 2D vector fields. Green's theorem only works in 2D. There is a 3D version of Green's theorem, which we'll talk about next week. But when we're doing Green's theorem for either line integrals or flux integrals, we only have a 2D vector field, and we're only in 2D. All right. Now, notice what the flux integrates over: the divergence. So remember, the day that we learned how to find the curl, we also learned how to find the divergence. So the flux and the curl are kind of like cousins, right? They're very closely related. What they do is they both use the vector field, except with curl, what we're doing is we're looking at how much of our vector, with a line integral basically, what we're looking at is how much of our vector field is going with or against our path of motion. So we look at the pieces that are tangent to our motion. With flux, we're looking at what's going through the surface. So we're taking the pieces that are normal to the path of motion. That's the only difference between the two. And so we use the curl for Green's theorem when we want the line integral. We use the divergence for Green's theorem when we use the flux integral. Other than that, it's the same thing. So if we wanted to do the flux integral for our example right here, and I'll do it in, let's do it in blue. So if we wanted to do the flux integral, our limits would be exactly the same. The only difference is what goes in here is now we're using the flux. So remember that the flux is the straightforward one. So ddx of this guy. So we got y plus ddy of this guy. So y plus 1 And we're doing the same order, so dx, dy. There's the flux integral. So they're very, very closely related because they're measuring slightly different things on the exact same path, right? One of them is using tangents, the other one's using normal vectors. That's the only difference. So I'm not going to bore you with an example of flux integral because it's basically the same thing. You know how to find flux. You know how to do double integrals. Like I said, I think you're going to really fly through this stuff. So again, a flux integral measures the flow across our path, right? Like I said, we'll be doing it with surfaces next week, which is a little bit easier for us to picture, right? Water flowing through a surface or some kind of liquid or gas going through a surface. The flux is measuring the amount of that. So we're using the normal parts. So we have two new guys today. Sorry, the symbol isn't showing up right on the, that's supposed to be a circle. It's right there. For some reason, they're not showing up nicely for me. It's a symbol that you see on a line integral because what it's talking about is the closed path. So I'll show you what it should look like on the board here. For curl, it's supposed to be a circle right there because what we're looking at is a closed path on C. And I want to also talk about this notation right here. Right here it is for curl. Now here's something that's interesting, and I want to parse this out because first thing you probably notice is, hey, it's a plus here, minus there, plus here. Why? Okay, so let's talk about that. All right, so we know to do a line integral, we do f dot dr because we're doing the parts that are tangent. Okay, so what are we doing then? Well, we're taking the two pieces, the two components of our vector field, and you'll see that like our book uses this notation M and N, you'll see that online. M just represents F1 and just that represents F2 with our parameterization in there. So what's happening is we're taking M, N, and dotting it with dx, dy. All right. And doing that dot product is where we get the, oops, put that in there, is where we get the M dx plus N dy, which again, for Green's theorem, ends up being the double integral of the curl because it's the curl, that's why it's the subtraction. All right, now for the flux, why is it that we get a minus in there? This is actually pretty cool. So now we're doing the vector field dotted with the normal vector. So F dot the normal. So when we're doing this, we're doing MN again. I mean, it's the same exact vector field, but we're dotting it with the normal vector. Now, how do we get the normal vector? We flip these, dy, dx, excuse me, not dy, dx, dy, comma, negative dx. That's the normal. Now, we're going to relate this back to something you have done before. What do you know about the slopes of perpendicular lines? The reciprocals, right? You swap the x and the y and you change the sign. And that gives you two things that are perpendicular. We swapped the x and the y and we changed the sign. So these vectors are perpendicular to each other. This is where the minus is going to come from. So that's why it's m dy minus n dx. All right. Now I show you these alternative forms because sometimes in the problems, what it'll say, it'll give you a vector field, it'll give you a path, and then it'll say calculate this. We need to know that when we see this, this is telling us that we're doing the flux integral. Okay. Again, not something you have to memorize, something I would expect you to put on your note card, but I just want you to be aware of these different representations and why this one came out as plus and minus, Whereas over here, it's minus and plus. And the only reason it's minus and plus here is because we're doing the curl, because we're going with our path, plus because we're doing the flux, because we're going perpendicular to our path. So the biggest thing, again, biggest takeaway from this slide is I just want you to be familiar with, okay, if the problem asks for this, F dot N, flux, because we're going perpendicular. F dot T or F dot dr is telling us a line integral. Okay. Just so we know what we're being asked to do, because both of these are easy, right? We set them up for the triangle problem there, no problem. But we want to make sure we're answering the right question. So that was just a little bit on the notation. That is Green's theorem.